Object 4's profit and weight are 1, 9. So I'll have to add 1, 9 to 0, 0, 8, 6, 10, 16, 13, 21. If I add S3 with 1, 9, I'm going to get these values. Now, you are going to formulate finally S4 is merging of S3 and S31. I'll try to merge these two. And while writing, I have to write them in order. That also you have to remember. So I have written 0, 0. Then I have to write 1, 9. Then I have to write 1, 9. Then I have to write 8, 6 in the increasing order of their profits. Then I'll write 9, 15, 10, 16, 11, 25, 13, 21, and finally I am going to write 14, 30. Now you have got your S4 immediately after performing merging. Try to perform purging. This is merge and purge. So for that, 14, 30, I'll purge because capacity is more than 25. Okay, it's gone. Then I'll start applying a dominance rule. Dominance rule is the profit should be increasing, weight should also be increasing. So for that, I'm going to compare 0, 0 with 1, 9. Okay, I'll keep both of them. 1, 9. I'm comparing with 8, 6. Profit is increasing, but weight is decreasing. So 1, 9, I'll remove. Then I'm going to compare 8, 6 with 9, 15. Profit is increasing, weight is increasing, fine. Then I'm going to compare 9, 15 with 10, 16. Okay, I'll keep them. 10, 16, I'll compare with 11, 25. These are also fine. I'll compare 11, 25 with 13 and 21. Now you can see that these two are violating the rule. Weight is decreasing. So what should I do? I'll do purging, and for that, I'll have to remove 11, 25. Now when I remove 11, 25, these two are becoming adjacent. 10, 16, 13 and 21 are becoming adjacent. So I'll have to compare these two. If they're satisfying, I'll not purge. So finally, once this entire process is completed, this is the table that you have formulated. That is, you have formulated these sets. This is first step in finding an optimal solution to the given knapsack problem. Formulating the sets from S0 to S4. Once you have formulated these sets, from this sets, you are going to find out an optimal solution for the given problem. Now, what is the information that is represented in these sets? S0 represents an empty knapsack bag. S0 represents an empty bag. S1 represents two states of the bag. Either the bag is still empty or the bag is filled with item number 1. The bag is filled with item number 1. 2, 10 indicates that the bag is containing item number 1. So here, because object 1's weight is 2, profit is 2, weight is 10. Then, if there are two states, two current states, two possible states of the bag, and if I try to include object 2 into the bag, then you'll get 4 possible states. There can be an empty bag, still the bag can be empty. That means I have not included item 1 into the bag. I have not included item 2 in the bag. The bag is still empty. Or the second possible state, I have decided item 1 is included, item 2 is not included. Then third possibility, item 1 is not included, item 2 is included. Then last possibility, both item 1 and item 2 are included in the bag. So this is the current profit of the bag and this is current weight of the bag. Then these are the possible states after making a decision on third object. Maybe the bag is still empty, or you have decided that you'll include only third object into the bag, or you have decided that you might be including first object and third object into the bag, or you are including second object and third object into the bag. Then you might think, what about the remaining possibilities? I can add all the three objects, 1, 2, 3, all of them I can add into the bag. If I add all three into the bag, the capacity is exceeding 25. So I do not have any state where it includes all three items into the bag. That becomes infeasible solution. So I am taking only feasible solutions. For considering feasible solutions, I am performing purging. Right? So these are the 4 sets that I have got. From these 4 sets, I'm going to formulate the solution vector, and the solution vector will be in this format. The solution vector X is a set of values, zeros and ones, x1, x2, x3, x4. Each value for the object is either 0 or 1. 0 here indicates that item 1 is not included into the bag. Item 2 is included into the bag if its value is equal to 1. X3 is also equal to 1, so item 3 is included into the bag. Item 4, x4 equal to 0, that means item 4 is not included into the bag. So I have decided that out of the given 4 objects, I have selected only object 2 and 3 for filling into the bag, because that is an optimal solution and that will give me the maximum profit. Okay, now how did I get this 0, 1, 1, 0? This information I have extracted from the formulated sets, from the sets that I have formulated, S0, S1, S2, S3, and S4. From these sets, I have extracted this information of 0, 1, 1, 0. Now, if you remember the previous slide, where now whether which item will be included into the bag, which will not be included into the bag, I have to make a decision. For that, because we are applying dynamic programming, we'll make always decisions starting from nth object to first object. So I'll make a decision on x4th object, whether I'll include it into the bag or not. Then I'll make a decision on the third object. Then I'll make a decision on the second object. Finally, I'll make a decision on the first object, whether to include it into the bag or not. So I'm going to take decisions in the reverse order, starting from nth object to first object. In this order, I'm going to make decisions, right? So first I have to make a decision on x4 value. I have to make a decision. For that, I'm going to take the last pair from S4. The last pair, the last member of set 4. Because I'm making decision on X4, I have to consider S4 and S3. Okay, so I'm going to take what is the last pair in S4? It is 13, 21. So I'm going to take this 13, 21. I'm going to check whether it belongs to S4 or not. Also, I'm going to check whether it belongs to S3 or not. Now 13, 21, it belongs to S4. It is there here in S4. 13, 21 is there. It also belongs to set 3. 13, 21 is also there in the set 3. So this is the scenario. 13, 21 belongs to S4. 13, 21 also belongs to S3. So that means if 13, 21 is there in S3 as well as S4, then that means we are not going to include fourth object into the solution, because optimal solution is 13, 21. This we have got it in set 3 itself. From the first 3 objects itself, we have got our optimal solution with the maximum profit and the maximum weight. After including set number 4, there is no difference in the optimal solution. The optimal solution is still 13, 21. That means there will be no difference in the optimal solution through including the fourth object. So I have extracted the information regarding fourth object using set 4 and set 3. And I have decided that I am not going to include fourth object into the bag. That means x4 value will be equal to 0. X4 value will be equal to 0. Then I'll make a decision on third object, whether I'll include this object into the bag or not. So for that, I'm going to make a decision by checking set number 3 and set number 2. Okay, so the same item 13, 21, I'm going to check and find out whether it belongs to S4 or not, whether it belongs to S3 or not, and whether it belongs to S2 or not. So 13, 21 is there in S3, so it belongs to S3. But if you observe set 2, 13, 21 is not there in set 2. That means previously, before including object 3, the optimal solution was 7, 25. But after including third object, the solution became 13, 21. Right? So now that means we have to include third object into the bag. Now, whenever we are including third object into the bag, that means x3 will be equal to 1, because 13, 21 belongs to S3, but it does not belong to X2, then third object will be included into the bag. Now, whenever it is so, X3 will be equal to 1. Then continuing, whenever we have decided that third object will be included into the bag, you have to perform a minus operation. 13, 21 nunchi you have to subtract the values of third object. The values of third object, you can see here, it is profit is 8, weight is 6. So I'm going to perform subtraction of 13 minus 8, 21 minus 6. That will be equal to 5, 15. Now 5, 15. I have to check whether it belongs to S2 or not. Then what about its information in S1? So you can see 5, 15 is there in S2, but it is not there in S1. So this is the information. 5, 15 belongs to S2, but it does not belong to S1. Whenever such is the scenario, then you will include that object. Second object will be included into the bag. That means X2 value will be equal to 1. Whenever X2 value is equal to 1, so while going on further with the next step, I have to perform subtraction 5, 15 minus the values of our second object. The values of second object are 5 and 10. And if I perform subtraction, I'm going to get, 5 and 15. This is 5 and 15. And if I perform subtraction, I'm going to get 0, 0. Then I'm going to check whether 0, 0 is available in S1 or not. And it is available in S0 or not. It belongs to S1. It belongs to set 1, as well as it also belongs to set 0. That means I have decided that x1 will not be included into the bag. X1 will be equal to 0. So from these sets, I have tried to extract the information on each object, whether I'll include it into the bag or not. So you can see that now the solution vector is 0, 1, 1, and a 0. So this is the solution that I finally got, 0, 1, 1, 0. So I have selected second object and third object to include them into the bag. So this is how we are going to solve a given 0-1 knapsack problem using dynamic programming. So this is all the theory part for whatever procedure that I have used to solve the problem. This is the theory part for that. How to represent each state SI, each set SI represents all the possible states after taking a decision on the ith object. Then each state is represented as a pair of profit, weight values. Then you are going to make a decision on each i+1th object, whether you want to include it into the bag or not. Then once SI1 is prepared, then SI1 and SI, these two will be merged. So this is addition operation. You are going to add the profit and weight of the i+1th object to the states in the SI, and further you are going to perform merging and purging on SI and SI+1. And then merging, after merging is done, you have to perform purging. Purging, two rules. The first rule is that you are going to remove all the members from the set whose weight is greater than the maximum capacity of the knapsack. Then you are going to apply the dominance rule, where every pair of set members are compared, and it is observed that it is made sure that profit should be increasing, weight also should increase. If anywhere weight is decreasing, then you are going to purge the first item from the pair. Right, then this is the algorithm. This is the process where you are going to prepare sets. You are going to formulate the sets. This is the addition, and this is merging and purging. Once these steps are repeated and all the sets are ready, then you are going to extract the information on each item from the sets. So you are going to start taking decisions on the nth object, then n-1th object, and so on up to the first object. So you are going to take decisions in the reverse order from nth object to the first object. Then finally, after you trace back, that is, you take decisions from nth object to first object. Finally, you'll come up with a solution vector, which will be the final solution for the given problem. So the time complexity for this algorithm is 2 power n, where this 2 power n is the time taken for generating these sets. Because if you observe this entire algorithm, this step takes constant amount of time. All these steps will take constant amount of time. Only this is the variable part in the algorithm, which is the loop. And this loop will repeat for n times. And each time you are generating a set. And in one set, you are generating many members. So how many members you are generating and how many sets you are generating accordingly. If you remember set generation algorithm that you have studied in discrete mathematical structures subject, for generating sets, For performing union operation and continuously generating sets, it will take a time complexity of 2 power n, where n is the number of objects that are given to you. Okay, so this was regarding 01 knapsack problem solving using dynamic programming.